Hello everyone, we're going to go over homework number 17, so if you could have that out, and we're going to go through the problems that were assigned. You did skip a few problems on here, as was stated in the homework, so skipping problem number 1, skipping problems 4 through 6 as well, so we're going to go through the rest of them. I copied and pasted a few definitions from our last notes from 10.5 and 10.6 onto the homework here just as a reference. So we talked about the counting principle right here, which basically says you take the number of outcomes in each situation. If you want to get the total number of outcomes for the entire problem, you multiply the outcomes for each situation together. Now, we talked about permutations and combinations, which both use the counting principle, because they both talk about multiplying the number of possibilities in the first step and the second step and the third step. The idea with the permutation is it's a little bit more specific, so it's an arrangement of things in which the order matters. However, no repeats are allowed. Sometimes with the counting principle we work with repeats, but in a permutation we narrow that down a little bit, and it applies to situations in which no repeats are possible. Combination also does not allow repeats, but what's different about a combination problem is it's an arrangement of things in which the order does not matter. So we have to think about problems in which the order does not matter, because that really takes the number of things that would be in a permutation and divides out the repeats. We talked about in class how if I had assigned groups of people, and I had assigned 3 people in a group, no matter how I arrange those 3 people in the group, they're the same group. So I basically am dividing out all of the repeats, where back in a permutation, the order matters, so each group would be different. So we'll talk about that as we go through a few of these problems, particularly 2 and 3 on the front page here. So number 2 says, consider making a 4-digit ID number using the digits 3, 5, 8, and 0. How many ID numbers can be formed using each digit once? So you notice in this problem that it says use each digit once. So we know that no repeats are allowed. So that kind of puts it into the category of a permutation or combination because no repeats are allowed. But in this case, when you're doing an ID number, the order does matter, because the ID number, let's say these are our 4 numbers, the ID number 3, 5, 8, 0 would be a different ID number than, say, 5, 3, 0, 8. Okay, those two would be different ID numbers. So the order in which we put these numbers does matter. So basically, this is a version of a permutation then, because no repeats are allowed and order does matter. So let's calculate how many ID numbers would be possible. Well, instead of choosing from the entire 10-number set, we're saying that the ID number has to be using 3, 5, 8, and 0. So there's 4 numbers that we can use in the ID. So if I'm going to figure out, well, how many numbers are possible for that first slot in the ID, so let's say there's 4 spots in the ID here, how many possibilities are there for that first number? Well, any of these 4 could be the first number, so there's 4 possibilities for the first number. Let's say I used 5 for the first number, then how many possibilities are there for the second number of the ID? Well, now there's 3 numbers left for the second number. Let's say it's a 0. How many numbers are left for the third number? There's 2 numbers left. And then how many numbers would be left for the last number? Just 1. So the counting principle says that we can multiply the possible outcomes for each step of the process here. So although this is a permutation, we still use the counting principle idea with this, and we multiply 4 times 3 times 2 times 1, and we get a total of 24 possible combinations. Well, I'm actually going to not use the word combinations here. ID numbers actually is what this one is, so 24 ID numbers possible. All right, so let's move on to problem 2b. How many can be formed using each digit once and not using 0 first? So once again, it's kind of the idea of a permutation here, except for we can't use 0 first. So if we can't use 0 first, let's go back to our original numbers again. We've got 4 slots, just like the first problem, just like part A. But this time we can't use 0 first. So how many options do we have for the first number if we can't use 0 first? Well, we'd have to pick one of these 3 numbers. So there's 3 possibilities for that first slot. Let's say I picked the 3. Now, how many possibilities are there for the second slot? Well, now I can bring the 0 back in because it only says that I can't use 0 first. So how many possibilities are there for the second slot? There's 3 possibilities for the second slot. Let's say I used 0 as my second number. Now how many possibilities for the third slot? 2. And then how many possibilities for the last slot? 1. So how many ID numbers are possible if I use the 4 numbers given, but just eliminate 0 being the first number? I'd have to bring that in later on. So 3 times 3 times 2 times 1 gives me 18 possibilities. So if I can't use 0 first, then that gives me less possible ID numbers that I can create from this group. So I have 18. All right, C and D then talk about, let's see, how many can be formed if repetition is allowed and any digit can be first. So if repetition is allowed, that means that it's really no longer a permutation and a combination. So I'm pretty much using straight up the counting principle here and just thinking through how many outcomes are possible. So if repetition is allowed, how many, well, again, I've got 4 slots here, so maybe I'll do the same process as the previous problems. So if repetition is allowed, how many digits could I use in that first slot? Well, it could be any of those 4 for that first slot. And if repetition is allowed, how many of these digits could I use for the second one? Well, if I picked 3 for the first number, I could actually pick 3 again for the second number because digits are allowed to repeat. So I could use any of these 4 for the second number, any of those 4 for the third number, and any of those 4 for the last number, because I can repeat any of them, so there's always 4 possible numbers given this situation. So 4 times 4 times 4 times 4 is 256 possible ID numbers. So if repeats are allowed, then that gives me a lot more possibilities for the number of ID numbers I can create with just these 4 numbers, 3, 5, 8, and 0. D, how many can be formed if repetition is allowed but 0 is not used first? So this is kind of like B, only I'm saying repetition is allowed. So we've got 4 slots again for our ID number. I could pick any of these except I can't use 0 first. So I only have 3 possibilities to choose from for the first number. But once I get done with that first number, I can use any of the numbers for the second slot because it says repetition is allowed. And I could use any of those numbers for the third slot and any of those numbers for the fourth slot. So 3 times 4 times 4 times 4 gives me a total of 192 different ID numbers, assuming repetition is allowed. So in C and D, we're kind of just using the counting principle. And in A and B, we're using permutations, which again, permutations and combinations still use the idea of a counting principle. They're just a little bit more specific. All right, let's go down to number 3. Again, we're not doing 4, 5, and 6, so we don't have to worry about those. But number 3, suppose each student in school is assigned 1 locker. How many ways can 3 new students be assigned to 5 available lockers? Okay, so let's figure out, first off, there's 5 available lockers, but there's just 3 students that I need to assign. Okay, so I've got 5 available lockers, and I'm going to take those 3 students. How many possible lockers can I assign to this first student? So let's just name these students just for purposes of the problem here. So I've got Anab, and I've got Lucy, and I've got, let's see, let's go with Lamar. So I've got Anab, I've got Lucy, and I've got Lamar. And so how many lockers are possible for Anab? Well, if there's 5 available lockers, that means there's 5 possibilities that I could assign a knob to any of those lockers, okay? So once a knob is assigned to a locker, Now, how many possible lockers are there available for Lucy? Well, Anab already has a locker, and Lucy's not going to share that with Anab, so there's 4 possible lockers that Lucy could go to. Once Anab and Lucy are assigned to a locker, how many are available for Lamar? Well, he's got 3 left to choose from. Okay, there's 5 available lockers, so now there's 2 more lockers that no one is assigned to. So we're not going to worry about those because we just have our 3 new students, Anab, Lucy, and Lamar. So we multiply those together. 5 times 4 times 3 gives us a total of 60 possible ways that those 3 students could be assigned to those lockers. Now, if we think about this problem, this one right here would be back in one of our categories here. In this case, the arrangement, let's see, does not matter.